Okay, so I wanted to learn about manipulating sprites and using compute shaders in Unity. So I made this little 2D lighting scene, and this video is sort of going to be my notes on how I did it so that I can remember and maybe someone can learn from it. The lighting is calculated either with the CPU at 20 frames per second or with the GPU much faster. The algorithm is not quite complete, but it works. So this is just a sprite right here, the normal sprite that you can get from Unity with a script attached to it. And then in the sprite value is this environment that I just made in Paint. So I just drag this into here. The sprite renderer contains a sprite which contains the texture. So we want to be working on the texture. The sprite might also change, but the sprite renderer is the same. This texture refers to the original image right here, which is just grabbed from the sprite renderer. This is going to be the texture that we're creating. Create a new sprite where the sprite is this final texture. And then whenever we edit the final texture and apply the texture, then the sprite will be updated, and then the sprite renderer will show that new updated final texture. The texture inside the sprite is just an array of colors. So to edit it, you use set pixel, the coordinates, and then to a color. So this is the R, red, green, blue. You can also get the pixel here, like I'm getting the blue channel, for example. This is the slope variable, which serialized field so that I can move it right here, like this. We also have this render with the GPU boolean, which also is a serialized field so that we can switch between rendering the GPU with the GPU or with the CPU. The algorithm takes the opacity information from the blue channel, so I've just defined the blue channel to be the opacity of this image. The CPU and the GPU version use the same basic algorithm. It draws arrays from the top downward, and when they intersect areas of not full transparency, the rays decrease in brightness and then continue on. So in Paint, for example, so the first ray comes in at some angle. It keeps drawing onto the texture until it reaches a point of not full opacity. At this point, it draws 1 pixel more and decreases in value. So now the brightness has decreased slightly, but it continues along the same path until it hits another area of not full transparency. Brightness decreases again, and it continues again on the same path. And then the lighting algorithm does this once for every single diagonal ray. We have a ray for each pixel along the top edge of the image, as well as extra rays, because like if you want to figure out if the sun's at this angle and we want to figure out what's over here, we need a ray that comes in from the outside, like this, which means more rays coming from out here. So there's slightly more rays than the number of pixels on the top edge of the image. So this is how many rays there are. We set the X position to the ray number, Y position to the top of the texture, so start up here somewhere, and set the intensity to 1, so this is the brightness, right here. While we're above 0, 0 is the bottom of the picture. If we're outside of the image, just continue without doing anything. So like if we're over here, outside the image, we want to continue down until we get to the image. So every time I draw to the pixel, I decrease the Y value by 1, so I'm going down in the image, and increase the X value by the slope. So that will increase by a fractional amount, so it may round down to 0, but over time, the X position increases slowly. But to refer to an element of the texture, we need integers. So we set the pixel of X and Y to this color, so it's just white. It's just grayscale with the intensity of light intensity variable. And then the intensity of the light is scaled down by the blue channel of the pixel it's currently over, and then step forward. And that's repeated again and again. First it's repeated, it goes down each ray, and then to the next ray, and so on. So the CPU does it 1 pixel at a time. and so on. The CPU calculates 1 pixel at a time. First, it calculates one ray, and so on, and then the next ray. This has some obvious potential for parallelism by setting all the rays at the same time in the GPU. So that's what I intended to accomplish. You can't set all the pixels at the same time because the pixels below other pixels will be set depending on how much light gets to them, and how much light gets to them depends on the pixels above. But you can set all the rays at the same time. You send data to and from the GPU with a 1D array. So the texture, the final texture that we want to write to, has to be sent as a 1D array from the GPU. But that's fine because we know how to do that. So first we get the pixels of the texture. Get pixels returns a 1D array of pixels. So we have to know the width of the height to be able to figure out what the picture looks like. A compute buffer is how you send and receive data from and to the GPU. So we got to create a new compute buffer with enough space to send all the color data. So each pixel is 4 floats because of RGBA, and there's this many pixels in the array. So now we need to set in the compute shader all the variables right here, which you can see, like unlit world is a variable, width is a variable, and so on. So we can either set like a single variable, set it, int, set float, set texture, with here like ints, floats, and textures, or we can set a compute buffer, which is an array with set buffer. Call dispatch the shader with this, which runs it with this many thread groups. We're going to divide the number of thread groups by 64 because in each group is 64 threads, because we want the number of threads to be equal to the texture width. So divide by 64 here, multiply by 64 here. So once all the variables have been set and the number of threads per thread group, then this function runs. This is a similar function to the CPU lighting function, but instead of running two loops, two nested loops, we just have to run one loop because this is already iterating through the number of rays. So ID is the effectively the ray number. It's a thread number, but each ray is going to be a thread. So we set the original x position, id.x. ID is a three-dimensional int. We're only using the first dimension, so we only have to worry about x. So set x to the id.x, which is the same as setting ray to, as looping ray through all the values of the texture width. And then again we set y to the height of the texture. While y is greater than 0, we round it to the nearest int and then use the lighting algorithm. The only difference here is because we're working on because unlit world is a one-dimensional data structure. We have to be aware of that. So even though it's representing a 2D data structure, we just have to apply this instead of calling xint, yint. And then it's just a generic data structure. It doesn't know that it's representing color. So to refer to the blue channel, we just say Z because that's the third float instead of B, which is also the third float in a normal color data structure, which is RGBA. So once we've defined all the lit world, the lit world texture is what we want to write to. And once we've defined all the values over here, after this is run, then we want to set the render texture active to this render texture that we are working with, which is this same one right here, which then allows us to copy the render texture to the final texture using read pixels, which copies the active texture. And again, apply to actually apply it, and then release the memory of the color buffer over here, so that we're not creating new color buffers and then just endlessly using up memory. You can see the algorithm doesn't quite work. I'm not sure exactly what I did wrong, but it doesn't like the part of my algorithm where I start outside the picture and come in, because yeah, you can see that it just doesn't like it. And also you can see that the texture sort of stops updating once I get to, stops updating on the left side right here, once I get to a slope that's going strongly to the left. I'm not sure why this is. I've tried debugging it. I don't know, maybe it's a simple mistake, maybe it's something I don't understand about HLSL. Also, the algorithm is slightly different. The GPU takes into account the angle the light is coming through, so it's coming at a steeper angle. At a shallow angle, it goes this far into the water, and at a steep angle, it goes much further, whereas with the GPU, it's the same everywhere. But that's just a simple difference that I didn't implement yet.